started. So just reminders. So quiz 1 is due tomorrow, 11:59 p.m. in grade scope. And mini project 1 is due Monday, 11:59 p.m. And this you can do as a group submission in grade scope. That way all team members have access to whatever comments I make, things of that nature. So I know it's a little bit confusing because you have 2 different grade scopes going. The reason why is because the quizzes, I can link those directly to LMS, and that makes it a lot easier for me to do the final scoring. But for you to be able to do group submissions, then I need to have a separate grade scope so that you can link to those people. So, apologize for the little bit of confusion, but hopefully it's not too bad. So, last class we were talking about sensors, the different kinds of sensors that we have, some of the problems that you might have, and ways that you can characterize things like the error in your sensors. And so what we're going to look at today is one of the main applications for using sensors, which is localization. So localization is basically answering the question, where am I? And you can have this in both a local and a global sense. So you could say another way is to determine the robot pose with respect to a given map. Which we haven't talked about maps yet, but we'll do that after we talk about Kalman filters. So basically with localization, just pure localization, what we're assuming is that we have a perfect map and imperfect sensing. So you could think about this, maybe you're dropped in the woods somewhere and you have the map and you have to try and use the landmarks to figure out where you are based off of what you know from the map, right? And so you're assuming that this map is perfect, but you have imperfect sensing. So if you're just using your eyes and you're trying to judge how far you are away from certain objects, there's going to be a certain margin of error, especially if the object's further away. Determining are you 50 feet or 100 feet away from that might be a little more difficult than if you're 2 or 3 feet away from something. So you have imperfect sensing and a perfect map, and you're trying to figure out where are you relative to that map. And so this is also considered a state estimation problem. Now we said before, the state of our robot, we usually use XY theta. So our XY position in the plane, and theta would describe our orientation. So as I said, there's local and global localization. So the local localization, we consider this local because the uncertainty is bounded to the current pose. And with Local localization, we assume that the initial pose is known. And so where you have something like local localization is with dead reckoning. So this is where you estimate your location based on your speed, direction, and your travel time. With respect to your previously estimated pose. And so it's local localization because with dead reckoning, we're using just the sensors that are proprioceptive, so only measure relative to the robot itself. And so our uncertainty in where we are is relative to our actual pose, right? So if our robot is, say, in this position, well, we might actually be somewhere here, right? So it's relative to that based on the errors that we have from our sensors. And so for dead reckoning, we use odometry, so your wheel sensors, and heading, or you may also hear them referred to as bearing sensors. So the odometry gives us the speed, and the heading sensors give us the direction. And then our global localization. This would be where you're trying to localize, but your initial position is unknown. So one of the examples that I've heard before for trying to distinguish between the two is if you think of the game Pin the Tail on the Donkey. So if you know your initial position, so you have the donkey on the wall, and your idea is to put the tail where it's supposed to go. And say you stand over there, and then you close your eyes and you try and pin the tail on the donkey. So that would be local localization. So you know where you were to start with, but because your vision is obscured, you have to go purely based off of your motion, and so that's going to introduce some error. And so that's kind of a local localization. Global localization would be if you're standing there and then somebody spins you around, maybe moves you side to side, and then tells you to go pin the tail on the donkey, right? So now you have no idea where you started from, and you're still trying to figure out where you are relative to that point that you want to get to. So a little bit of a distinction there depending on what information that we have to start with. So there are a lot of problems that can come about with localization. So one of the first ones is that your sensors typically cannot directly perceive the state, right? So we have things like range sensors and bearing sensors, but they can't tell us the exact x, y, theta position that we're actually interested in. So what we have to do then is we need to estimate the state from the data. Another problem, which we've mentioned before, is sensor noise. So if we think about things like if we're doing some kind of color detection, you have hue changes due to changes in illumination. If you have something like a camera where you're trying to do some kind of motion analysis, well, there's a chance that you could have jitter in your video feed. So if there's some vibration in your mobile base, and that translates to the camera, and then you have this extra motion that you're detecting, which is not what you're actually interested in. We also have the problem of sensor aliasing. So that's where you have multiple environment states. That can give the same sensor reading. And then, since typically the way that we do localization is to use the odometry sensors, and our odometry has a lot of errors due to environment changes. And the resolution of your sensors. And another problem with the odometry is that to figure out position, we use integration, which basically means that we accumulate that error over time. So as we have these environmental changes which affect our odometry readings, we're using that integration, and so as we go further and further, we're going to get more and more error. So typically when we're trying to do state estimation, then we want to do it recursively. And so first what we do is we have some kind of prediction, which is based on our proprioceptive sensors. So basically we use our odometry and our bearing sensor to give a sort of prediction of what we think our state is. And then, based on that estimate, we do a correction. So this is where we use those external sensors to do some kind of correction of our prediction. And so we could use landmarks, and another thing that we might use is what's called loop closure. So what loop closure is say that you're wandering around in the woods, and then all of a sudden you come across a stone or a tree that you've already seen before, right? And so that means that you've completed the loop. And so you can use that. So if you say that you're trying to do a square, and then based on your loop closure, you find out that you're further away from that than you expected, that's the way that you can correct for any kind of odometry drift errors. And so you recognize a previous location, and you use this to help correct for drift. And we have a similar kind of idea when we talk about mapping, that when you get back to a certain location, that this can tell you things such as hallways and rooms, so it can help you align the errors that you had based on your map. And we'll also see actually this sort of recursive state estimation when we talk about Kalman filtering. So Kalman filter actually uses a similar type of thing where it predicts based on the model that it has, and then it does a correction based on whatever sensor measurements you have. So this kind of recursive idea to keep decreasing the error is something that we'll be seeing again next class. So one of the errors that's the biggest concern for our mobile robots is what we refer to as drift error. So this is error in the robot angular orientation. And so the question might be, why is that one of a particular concern? Well, if we think about, we have our XY here. And then let's say that we want to move straight along X, and we assume that our theta doesn't change, right? But if in reality we have some delta theta here that's offset, so our desire is to move straight in X, then what we'll find is that the error in Y is d sine delta theta, where d is our linear distance that we're traveling, and delta theta is that change in orientation. And so this type of error is actually a non-linear growing error. And so what this means is that if I have my robot here, as I move along, where it actually is could be somewhere in this region. I move further, and now, well, it actually could be somewhere here. And as I go even further, we have this growing uncertainty. And so if you want to see a good example of this, since I haven't got it fixed yet, Robot 6, if you go through and you tried to do just a plain linear motion, you will see that there is a significant curvature, right? And the further you go, the worse it gets, to the point where it almost goes to a 90-degree within the span of the pads that we have set up. So, even things that are not working well are good learning opportunities. So you can see a good example of that in the lab. Now we'll talk about estimating the state from sensor data. So there's a few different scenarios that we could have. We could have the static problem. So we have y, some function of the state with some noise. So this is our measurement, some function of the state, and then we have some noise in our measurement. So if you have a case like this, then if we assume F0 and some statistics of V are known, then we would need more sensors than states to be able to figure out what our state is. You can almost kind of think of this as like a one-shot estimate. So you're in whatever state, you take all of your sensor readings, and then based on those single set of sensor readings, you're trying to figure out what your state is. And so for that reason, you need to have more sensors than states to make sure that you have enough information to be able to backtrack. The dynamic problem is where you take into account the change in the state and then your measurements are based on the state. So we'll assume F0, Fx, and our statistics of V and W are known. Then what we can do in this case is we use sensor data from multiple time instances. And since we're using multiple instances of time to do our state estimate, then the number of sensors may be less than the number of states. So look at how you would solve these problems. Just first in notation, so I'll say X is the actual state. When I put this hat or caret, whatever you want to call it, over the top, that is our state estimate. And then when I use the subscript, that means that we have discrete time. This is state at time instance k. So for the static case, if we want to figure out our estimate of our state, basically what we're trying to do is we're trying to solve this minimization problem, where we're trying to find the estimate which minimizes the error between our measurement and what would be expected based on the state. Right? Because if we had the actual state, and we're assuming that we know how the state relates to the sensor measurement, if this was the correct state, then this would go to 0. So there would be no error, that what we expect based off of the model would match our measurement. And so this minimization problem, we can actually augment this a little bit. So because if you notice that we also have this noise up here, which we don't take into account here. But if we know something about the noise, we can actually incorporate that. So if we know the relative magnitudes of V, and so relative magnitude because V is a vector in each element relates to one sensor. Then we could write B as this capital B, this matrix B is 1/2, Bn. So Bn is just a vector of ones. So basically the idea here is that Bn would almost be like representing a ball in the n-dimensional space. And then this matrix B1/2 would shape that ball into an ellipse, which would reflect this vector B. So the idea is that B kind of captures the relative uncertainty in each of the sensor measurements, right? So you're going to have some sensors that you're more confident in reading and some that you're less confident in. And so what we can do is based on this V, this V matrix, we can modify our minimization problem to incorporate the inverse of this matrix, y minus f0 x hat squared. So what does this actually do for us? So why do we include this? It gives higher weight to our sensors with less noise. So let's say, for example, that we have our vector is 0.1, 0.5, 1. So we have a lot of noise in the last sensor and not as much noise in the first sensor. Okay. So our V1/2 would be 0.1, 0.5, 1. And then our V inverse would be 10, 2, and 1. And so what this means is if we were to plug this in here, it would mean that our first sensor, we really want to make sure that our estimate is close to that sensor measurement because we're really confident in what that sensor is telling us. The last one, it's probably good information, but we're not as sure if that's actually helpful to us. So we're going to try and match that one, but if we're not that close to it, we don't mind as much. So this is a way that we can take into account those sensor errors if we have some knowledge of how they relate to each other. And if we were to have something like V is just some kind of scaling of this, our capital V would be the same because we can just kind of factor that out. And so basically what we can see is that higher value where sensor noise is smaller. So how do we actually solve the minimization problem? Depends on the nature of this f0. So if f0x is linear, so you have the case that y equals cx, where c is just some constant matrix. Then we can use the pseudo-inverse. So our estimate of x is just c pseudo-inverse y. And The error in the estimate is 1 over sigma n, norm of the noise vector v, where sigma n is our smallest singular value of c. And so if you go through the math, you can prove this relationship. So it kind of comes from the fact that the singular values of the inverse are just the inverse of the singular values of this matrix. And looking at the norm of each side, you can come to this conclusion. And so what this tells us is that a couple of things. So to be unique, we need C to be a tall matrix. The full column rank. So why is that? Let's call this a trivial null space. Otherwise, what we would find is that x hat, where x hat is our estimate based on this pseudo inverse, and then we could add an x hat, which is in the null space of C. That's also valid. So this is in null space of C, and that would be from our C pseudo inverse Y. And so then we no longer have a unique solution because we can add any vector from the null space and still have that satisfy our relationship. So that's one of the conditions on C, and we also want a large smallest singular value in C, and that way we have less error in our estimate. Right. So if this is really large, then that helps to reduce the error. So that's something that if we know this matrix C, that we can take a look at it, and that gives us some indication of how well we're able to estimate our state based on our measurements. Now, if f0x is nonlinear, now we have to try and solve a nonlinear least squares problem. So in the linear case, we had simple least squares, and we know the solution to that is just the pseudo inverse. But now that we have a nonlinear system, how would we actually do that? So if we let the objective function be, I'll use a script v, because you'll see v a lot for objective functions, because it also ties to the guy's name at the moment, but it's something that you also use for proof of nonlinear stability of systems. So you'll see v used a lot. I apologize that we keep using v so much, so I'm trying to distinguish as much as I can. So if our objective function v 1/2 y minus f0 x hat squared. All right, so we're trying to minimize the error based on, so we're trying to find the estimate of x, which minimizes the error with our measurement. And then we could compute the derivative of that b as this somewhat complex thing here. So you notice that y and this f0, these are vectors, and x hat is also a vector. So this is actually a vector derivative. So keep that in mind. It's not quite as straightforward. If you're not really familiar with vector derivatives, usually my suggestion is to write it out first. So just assume this is maybe a 2 or a 3 by, and then actually do out the square and then compute the derivative that way. Kind of give you some insight as to where these transposes and whatnot come about. And this here, our gradient with respect to x of f0 x hat. So this is a derivative, the first element of our f0 with respect to the first element of x. Evaluated at x. Derivative of, we'll say that there's p elements of f0, taking the derivative with respect to the first element of x. There's the first element of x, to the last element here, 0p, and x. So my notation here, so f0 x, we'd have f0 1 to f0 p, and then our x we'd have x1 to xn. Anybody remember what you might call this matrix from calculus or robotics 1? Yeah.
It's not a Jacobian, is it?
Yeah. Yep. So Jacobian matrix, because it relates, it's like the derivative of each of those elements with respect to each of these elements here. And so I point that out because we're going to see in a minute that the way that we're solving this nonlinear equation here, this nonlinear minimization, is actually going to relate very closely to what we did for inverse kinematics in robotics 1. It's the same, mathematically, same kind of idea, just maybe slightly different application. So we actually solve this iteratively. And as follows, if I just put it in kind of really broad terms, is that while our objective is greater than some number, we update our estimate by taking the previous estimate, and we have our update parameter, and we update with this change in x hat. And so what we can use for x hat, there's a few different methods. So we have gradient descent. In that case, we have our x hat dot is this gradient of f0 transpose y minus f0 x hat. We have Newton's descent, which is very similar to the gradient descent, but instead we use the pseudo-inverse instead of the transpose. And then for those that remember, the other method that we'd used for inverse kinematics was the damped least squares, or you might also hear it referred to as the Levenberg-Arkard method, where we have x hat dot is equal to epsilon I plus gradient x f0 x hat transpose gradient x 0 x hat inverse gradient x f0 x hat transpose y minus f0 of x hat. So some things to note is that you need sufficiently small alpha k for the gradient descent. Newton's descent has stability issues near singularity. So why we would like Newton's descent is because that would be our best approximate in the least squares sense. But when we get close to a singularity, so when this starts to become singular, so the inverse comes closer to not existing, then this can blow up really into really high numbers. And so as this starts to go up, then you have to really decrease your alpha k. And the alpha k, we want that to be sufficiently large that we have fast enough convergence, but it also has to be pretty limited because of issues with each of these methods. And so the damped least squares tries to give you a trade-off between these two. So what it does is it adds this epsilon term here. So the damped least squares is basically the pseudo-inverse with what we call a regularization term, which is that epsilon. Right. And so what this does is that when our pseudo-inverse would be close to singularity, we have this epsilon here, which prevents this inverse from actually becoming singular. So it just gives us that the diagonal. So this I is the identity matrix. And by adding that, we can help mitigate some of the effects of what happens when we get near singularity. And so we want epsilon should be relatively small because we don't want it impacting too much our pseudo inverse that we're using. And if epsilon is smaller, it's actually closer to the Newton method. And if it's larger, it's actually closer to the gradient descent. And other problems that we have with those first two methods is that the gradient descent may get stuck in a local minimum. And I said already here, because of those stability issues, that Newton descent may need to limit that gain, that alpha k. And so the damped least squares tries to balance the two. So let's look at, let's say that we're trying to determine our state using range sensors. They're going to say that they detect distance to known landmarks. So we'll talk about landmarks a little more when we talk about maps, but basically these are things in the environment where we know the exact position of them, and we know where they are relative to each other on the map. And so we're going to assume that we have some range sensors which can tell us the distance to these known landmarks. So basically our sensor measurement then is y is the distance between PL and PR. So this is landmark position, and PR is the robot position. So if we have one sensor, in the 2D case, what that actually tells us is a location on a circle. Why is that? If we have our landmark here, and all we have is a distance measurement, which we'll say is D, so our robot could actually be at any point on that circle. If we have a 3D case, then it would be location on a sphere. So same kind of idea, is that it only tells us the distance from that landmark, so we could be anywhere around that landmark at that distance. If we have two sensors, and in the 2D case, we have two distinct points, and in the 3D case, we have location on a circle. So let's say we have one landmark here, and we measure some distance, and we have some landmark here, and we measure some other distance. So you can see that there's two possible points in this 2D case where our robot could be, and we'd get those two measurements. And it might be a little bit harder to visualize in 3D, but if you have two spheres intersecting, that actually gives you a circle. And one thing to note is that when we're using the range sensors like this, we get position only. For those cases. So what if we had 3 sensors? Then in the 3D case, we have two solutions if they intersect. And actually what you get is a cone and plane intersection. So for those of you that took Robotics 1, you would use subproblem 3 for that. If you remember from inverse kinematics, we had these different geometric subproblems. So it turns out that you can use these subproblems also for getting your position estimates based on these range sensor measurements. This is 3D case. And you could also, let's say that you know some information ahead of time. So say we know that the robot is on a plane, then we could have 2 sensors, plus the knowledge that we're on a plane, and then that can give us 2 solutions. I use that abbreviation a lot in my notes. 2 solutions makes sense to me, might not make much sense to others reading my notes, so fix that. 2 solutions if the spheres intersect. And so basically you can use some a priori knowledge to reduce the number of sensors that you need to help reduce some of the ambiguity in where you are. So all of these give us some position. If we wanted to get orientation too, what we could use is triangulation. And so we get our heading, bearing, orientation, whatever term you want to use. So you can get that information as well. So what you could do is use robot motion to try and figure out your relative heading. So based on the way your robot is moving and the measurements that you're taking, you can get a rough idea of your heading. Or you could measure the range on multiple points of the robot. So let's say, for example, that you have a room here. And let's say that you have emitters in the corners of the room. So these emit some kind of signal. And then you have your robot down here. And let's say that you have 2 receivers on it. Right. And so if you have some setup like this, then you can get position and orientation. with our 4 range measurements. So can you think of any potential problems you might also run into, though, with these types of methods? So let's say I have a landmark here. And let's say that my robot's here. And I have my other landmark here. Let's say they actually have noise in the measurement. So this one actually thinks I'm somewhere here. And this one thinks I'm somewhere here, right? So if we have noisy measurements, then we can actually have cases where our circles or our spheres no longer intersect. And if you have a case like this, what happens if there's, say, some kind of cabinet there, and the robot happens to be right next to the cabinet? Now all of a sudden you've lost line of sight to one of your sensors, right? And so even though you had sufficient number of sensors to be able to tell your position and orientation, now all of a sudden basically one of those went offline, and now you've lost some of your critical information. So something that we'll see when we talk about Kalman filters is that the Kalman filters use the prediction, and they also use update based on measurements. But because you do it recursively, if for some reason you lose sensor measurements for one of your time steps, you just skip the correction part. So you just do the prediction until you get those sensor measurements back. So that's why Kalman filter you see used so much, because it helps a little bit with robustness to some of these issues. Let's say if we tried to do the same kind of idea with bearing sensors. So let's say that we have our robot here. So use an arrow so we know which way the robot is going. And so it's forward motion along the x direction. And then we have some landmark here, which has a bearing sensor on it. And so this sensor would tell us the angle between the heading and the bearing landmark. And so what we're actually interested in is theta. So that's the theta relative to our fixed world frame. And so the bearing sensor gives this phi, which is the angle between the vector, which is PB minus PR, so this vector here, and our heading direction, xm. And our xm is some rotation about z of theta ex. So that kind of describes the orientation of this xm relative to our world frame. And so we can actually relate the positions, PB and PR, PV minus PR to our XM. Like so. And so I do have some slides that I can share if you want a little bit more details on how you can derive actually getting the thetas, how many sensors you need, things of that nature. But I'll just kind of give you the punchline that if you have two bearing sensors, so it's a lot of geometry, so figuring out laws of cosines and triangles and all of that, which I can share if you're interested. But if you have two bearing sensors, what it gives you is it gives you possible PR locations, which are actually on an arc. So what you'll have is basically your possible PRs are somewhere on the arc of a circle. So there are different constraints which prevent it from being a full circle and limit what that is. But the main idea is that you can have some arc based on two bearing sensors. If you have three bearing sensors, then you're looking at the intersection of two arcs. If you have a combination of bearing and range sensors, what you can do is one range and two bearing will actually give you two solutions for position and orientation. And you actually get an intersection of an arc and a sphere. So that's actually a subproblem 3 solution again. And if you had, say, 3 range and 1 bearing sensor, so what we had before is if you had 3 range, then you could get position. If you add this in, then you can get your position and orientation. So I guess kind of the main takeaway of this section is when you're trying to figure out where to place sensors, what kind of sensors you want for your system, it actually turns out to be a pretty complex problem. So you'll see a lot of different research articles looking into, what's the optimal way to basically set up your environment to be able to get the accuracy that you need for whatever your application is. So there's lots of different sensors out there, lots of concerns depending on how they do their measurements, ways that the environment could impact those measurements. And so a lot of thought goes into actually choosing how many and where. So we'll talk about the way that we describe the state. So up to now, we have described the state as our xy theta, which is a continuous representation. But something that we'll see when we talk about mapping is that you could also describe it discretely. So we could describe this discretely as well. So if you think about, say, if the map that you're looking at is a grid, so if you're to look at, say, in the last space where we have those squares, you might describe the where am I according to which square. right? And so sometimes what we'll see with mapping is that you can have these things called occupancy grids. So basically you split up your space into a bunch of squares, and then where you can and can't be, you can fill in all the spaces where there's an obstacle or something in the environment, and so then you can plan around those blocked off sections, right? So there are some pros and cons depending on if you use continuous or discrete representations. So continuous versus discrete. So our continuous, our precision is bounded by the sensor data. In the discrete, our precision is bounded by whatever level of discretization we use. In the continuous, we usually have a single hypothesis. And I'll show you what I mean by that in a moment. Whereas in the discrete, we usually have more of a multiple hypothesis situation. In the continuous case, we can get lost when we start diverging. In a discrete case, if we start to diverge, it just converges to another cell. So we don't usually have a problem of being lost. If we diverge a little bit too much, then we just kind of convert into a different cell. The continuous is a pretty compact representation. And uses usually a reasonable amount of processing power. Whereas a discrete case, that can require more memory and processing, although it's less so if we use topological maps, which we'll talk about those when we talk about mapping. Right, so if you have a discrete grid, then you have to have some way of characterizing each of the grids in the space. So that can be a little bit harder to code that up versus just having a continuous XY theta. But there are pros and cons depending on the situation. So the way that we describe where we are, what we call those is belief representations, which is basically where do I think I am? And so that's where this hypothesis term comes in. So if we have a continuous representation with a single hypothesis, then what we would have is if, say, this axis is our position, and this axis is the probability of that position, then if it's a single hypothesis, then we say we're most likely at this position or some place really close to it. If we have multiple hypotheses, then you can probably guess what this is going to look like. So basically, we have a couple different locations where we think we might be, and we have some probabilities that we're at each position. And so when we have something like this, let's say that we have a hallway here. Let's say our position 0, 2, 3. Let's say that we have a hallway, we have a door between 2 and 3, and we have a door between 5 and 6, and a door between 9 and 10. And we're going to say that our robot here, we start off at wherever our initial position is, and then we're going to say this is 2, and this is position 3. So when we're at position 1, basically we have no guess of where we are. Right. And then we move a little bit and we see the edge of the door. Right? And so now when we're at position 2, we say, well, we see that we're at the edge of a door, so there's a chance that we're somewhere before 2. But there's also a chance that we're somewhere before 5. And there's also a chance that we're somewhere before 9. Right? And so then we move a little bit further and we've seen that the door ended and we see the beginning of the next door and that it was a shorter distance than between these two doors. And so based on that, we might have then that our confidence grows that we're at this location. So this is an example of using the environment to improve our state estimate. And so basically what we'll see with Kalman filters is that we're always going to have this sort of ambiguity as to where we are, but by using our model and using our measurements that we can reduce this error. And so we can kind of pinpoint a little bit closer as to what our actual state is. So I guess next class then we'll start with a little bit of probability review, since it's probably been a little while since you've seen some of the terms. And then we'll go into the actual Kalman filter. And since I kept you a couple minutes yesterday, or Monday, I'll let you have a couple minutes early this day.